Welcome again. So in this session, we introduce the third method of approximating solution to the nonlinear equation, f of x equals to 0. And this method mostly is applied when the structure of the function f of x is easier to differentiate. So the key step or the key thing is that for you to apply Newton-Raphson method, then your knowledge on differentiation is actually key in helping you to come up with a formula. So, and say this is another method. Of finding isolated roots to the equation f of x equals to 0 when the derivative of f of x can be computed. So let's see the derivation of the method. Derivation. Let x equals to x naught be an approximate root of the equation f of x equals to 0. Let x equals to x1 be the exact root of the equation f of x equals to 0. So this is to mean that when we put x1 into the equation, then the equation is satisfied. F of x1 is 0. So let's call this one question 1. Let x1 minus x naught equals to h be the difference between x1 and x naught that is very, very small. That the distance between x1 and x naught is given by a very small value h. So then we have, so if x1 minus x naught is h, then we have x1 itself is x naught plus h. So let's call this one 2. Substituting two in 1, we get, so whether it's x1, we put x naught plus h. So we'll have f of x naught plus h equals to 0. Let's call this one 3. Now we expand 3 in Taylor series. i.e. f of x naught plus h will be given by f of x naught plus h over 1 factorial f prime at x naught plus h squared over 2 factorial second derivative at x naught plus h cubed over 3 factorial f triple prime at x naught plus other several terms. So let's call this one equation. However, this is equals to 0. Let's call this one 4. Now, since h is very small, we neglect second and higher order terms in h. Actually, this is what we call to first order approximation. Then 4 becomes f of x naught plus h f prime at x naught is equals to 0. So which means that we make h the subject and we get f of x naught equals to f of x, h equals to f of x naught over h f prime at x naught. So let's call this one number 5. Then equation 2 becomes, remember equation 2 is x1 equals to x naught plus h. So therefore equation 2 becomes, using equation 5 in 2, we get x1 equals to x naught and then plus h, but h, remember there's a negative sign here, is negative f of x naught divided by f prime at x naught. So this is what we have. And then the above value x1 is closer to the root of f of x equals to 0 than x naught, which was the first or the initial approximation. Similarly, if x2 is or denotes better approximation, starting with x0, starting with x1 now. Then we have, if we had called this one number 6, just taking the structure of 6, then we have from 6, x2 equals to x1 minus f of x1 divided by f prime of x1. Similarly, x3 will be given by x2 minus f of x2 divided by f prime at x2. And then x4 will be given by x3 minus f at x3 divided by f prime at x3. And the trend continues up to xn be given by xn minus 1 minus f of xn minus 1 divided by f prime at xn minus 1. And then xn plus 1 is equals to xn minus f at xn divided by f prime at xn. So this is the method or the formula that we use to approximate the solution of the equation f of x equals to 0 by the Newton-Raphson method. So one key thing that you see in this method is that you have to calculate the derivative of the function. So that is actually the main disadvantage of this method, that if you don't know how to calculate the derivative of the function, then you can't use it to do the approximation. Next session, we'll be doing an example to see how to illustrate the Newton-Raphson method. Thank you.